And we're back with video 2. So in a series walking through the 2026 AP Physics 1 algebra-based version J released free response. In case you didn't watch the other one where I gave more of the setup on this, I also have over here a grading rubric that I have put together. This is not the official one because we're right after the exams took place, so that hasn't actually been generated yet so far as I know, because it'll be updated at the actual reading, which happens in a couple of weeks. So on this, we'll be going through the grading rubric. Part of that is also so for anyone who did the exam, maybe you're watching this video in a recap of it to see how to actually solve it, but I'm also trying to predict what the partial credit is. So you'd have an idea of, if you didn't get the full answer, about how many points you might get. Okay, so jumping back in, question 2. I love question 2. Question 2 is a collision one, and this is one that we've done a decent amount with my classes, so I'm hoping that they do very well on it. We're going to find out. Two small disks, R and S, are on a straight horizontal track. At time t equals 0, disk R of mass m naught is located at position x equals 0. Disk R is initially moving with speed v naught in the positive x direction. Disk S of mass 3 m naught is initially at rest as shown in the top view in figure 1. Frictional forces are negligible. So we got a frictionless table. We got these two things, disks or a ball or whatever, that run into each other. So in this case, disk, because we'd have them sliding. We don't want them rolling. And we've got a top-down view, as it says here. Forgive me if I refer to them as a ball. I'm used to drawing these things in a similar way. At time t equals t1, the disks collide. Immediately after the collision, disk R moves with speed 1/2 v naught in the negative x direction. Always pay attention to your directions. They are giving us correct information by saying speed, but they're making it a little bit tougher. It would have been easier if they said a velocity of negative 1/2 v naught. But we're checking that you all can apply the correct things by being given different types of information. Okay, as I've told my students many times, many of you are probably my students, in this case, when you see collisions, your brain should immediately go to momentum. Momentum is the physics of collisions. Okay, note, figure not necessarily to scale. Let's see, so this was on last year's, or one very similar to this, I should say, was on last year's APC exam, and I actually put several of these on quizzes and tests this last year, so fingers crossed that worked well for my students. The momentum vector diagram in figure 2 represents the momenta of disk R and disk S before the collision. In this case, we've got, this one is 1, 2, 3, 4 units to the right for disk R, and disk S has no momentum because it's sitting stationary. Remember, your momentum is your mass times your velocity. So they've set up an arbitrary scale on this, but it's one that we need to maintain, that the initial momentum of disk R is 4 units. We're going to come back to that. Okay, draw. Our instruction word is draw. Arrows on figure 3 to represent the momentum vectors of disk R and disk S after the collision. Each arrow must start on the dot and point away from each dot. Make certain that you do not leave space between the dot and the arrow. Those were the instructions that they gave in the past for free body diagrams, so make certain that there's no gap. Start on the dot and then draw away from it with your arrow in the direction that the arrow is pointed. If the momentum of either disk is 0, write P equals 0 next to the dot. Otherwise, you would leave it blank. It's an important rule in test writing that we do not have something where the correct answer is to just leave it blank, because then we don't know if you didn't get to it, and you shouldn't get points if you didn't even solve it. So just as a side note, in case you're wondering why they would have us write that out, you have to give some indication that you intend for it to be 0. So that's pretty common on the exams. Draw the length of each arrow to represent the magnitude of each momentum consistent with the scale used in figure 2. Here's where they're telling us that we got to make certain that the scales are correct. Okay, so on this, here's where my immediate thought is this. I've got R coming in like this with an initial momentum of m naught v naught positive because it is moving to the right. We've got disk S, which has 0, so plus 0. My total initial momentum is m naught v naught. Afterwards, I've got R moving backwards at 1/2 v naught. So it has negative 1/2 m naught v naught And we have some unknown momentum for disk S, which we will come back to. In fact, the way that they've set this up is actually great because part A, when you complete it, will give you insight into how to go about working part B. Okay, one thing that I'll bring up is this. So looking at this and getting the scale, we know that we started with m naught v naught, and that was equal to 4 units. Okay, great. Well, if I need something to be 1/2 m naught v naught, how many units should it be? Well, 1/2 of this would be 2 units. So on this, for my graph, I would need, here's my dot. I need to draw an arrow that is 1, 2 units to the left. I'm going to draw a few more so that we can see them there. I would draw this on the actual diagram, which you would in your exam booklets, but I have to kind of draw it here. I need 2 units for the correct scale, and I need it to be to the left because we are told that that is in the negative x direction. Please note, we didn't actually have to use any physics to solve for any of this, at least not yet, though we do need to be familiar with momentum and how to work with it. Okay, so this is what we should end up with for disk R. It should now be going backwards with half the momentum that it had before. The difficult part is going to be S. Okay, here's where we have to start bringing in our physics knowledge. We have the total momentum of our 2-disk system before the collision was 4 units plus 0 units. We have a total of 4 units, which means we must have the same total for our 2-disk system after the collision to conserve our momentum. So in this case, I started with 4 units total. I need to end with 4 units total. Now that I have identified that this one is -2 units, I need -2 plus question mark will be equal to +4. With this, you can solve it and fill in that this needs to be +6. So we need to draw this all the way over to 1, 2, 3, 4, 5, 6. Not my best drawing ever, but when I go back over here, please note 1, 2, 3, 4, 5, 6. The correct answer would be drawing it all the way to the outside edge. Last year on the APC mechanics exam, where they had a similar one than this, they actually had a few more dash marks than what you would need in there. I think part of this is, the correct answer is, if students were in a hurry and just drew it all the way over there without counting it, they would probably naturally stop at the edge of it, so it may have been AP1 doing some favors to the students. Keep an eye out for this in the future. If you're in my class, I'm not going to be that easy on you. I'll probably put extra ones so that you have to actually count them out. One thing that I've also been doing on this, for every third unit, I would actually make it darker so that you can kind of see and it's a little bit easier on the eyes. It was kind of difficult for me to count all these up to know for certain. Okay, so on this, we have how I'm breaking down the points. I think that this is worth 3 points. I apologize, this is a translation between representations. Part A is usually you will create something, be it momentum diagrams, be it free body diagrams, be it energy bar charts, or motion diagrams. But the first part, you will make something, and it will pretty much always be worth 3 points from what I've seen. The first point is for drawing an arrow for disk R to the left. In other words, I tied 1 point to properly identifying that momentum is a vector and that you would represent that the momentum for disk R after the collision is to the left. I also thought that you would get an additional point for drawing an arrow of length 2 units for disk R. In other words, being able to take the 4 units and cut it down to 2, being able to work with having half the velocity. In this case, I made these 2 separate things. So I think that if you drew a 2-unit length to the right, you would get 1 of the points, but not both. Again, this is educated guessing on how I would set up the grading rubric on this, but I think we'll actually be fairly close to what AP actually does. The last one would be for an arrow for disk S that is to the right, or actually more to the point, I think I just said the arrow is such that if you add this one and whatever you drew for R, that they come up to +4 units total. In other words, for the second one, or the last point, for the second disk, I think that you would get the point on that basically for giving it whatever momentum was appropriate to conserve the momentum. Part of that is also because that's what they would expect you to do with the momentum diagram to know how fast it's going, which is what we're going to do in part B. You would actually have to do a whole bunch of additional work. In this case, we can correctly predict that it needs to be 6 by conserving the momentum with our momentum diagrams. So I think that that's what the last point would be, and this is very similar to what we had on the APC Mechanics exam. I think it was it may have been question number 1 last year in 2025. So you're welcome to take a look at that for a different AP question that also had momentum diagrams on it. Okay, moving forward, part B. Part B for a translation between representations is pretty much always derive. I think it's kind of locked in as that, and it will be worth 4 points, I think, every single time. Starting with conservation of linear momentum. Hey, it's giving you a hint of what to do. Derive an expression for the kinetic energy of disk S immediately after the collision. Express your final answer in terms of m naught, v naught, and physical constants as appropriate. Begin your derivation by writing the fundamental physics principle or an equation from the reference sheet. Well, they already told us to start with conservation of linear momentum, so going through, I'm going to do that. We've got my total momentum of my system initially is m naught, v naught plus 0. This is from disk R, this is from S. We have over here, we know that the final momentum of disk R is negative 1/2 m naught, v naught. Remember the negative, momentum is a vector. You must keep track of direction. Plus 3 m naught, I'm going to call this Vs, the speed, or more accurately, the velocity of disk S. Okay, great. So this gives me m naught v naught equals negative 1/2 m naught v naught plus 3 m naught Vs. I'm going to show a little bit of extra steps in here. You could easily skip over this intermittent one, but I know sometimes making the zeros go away can be useful. One thing that I would recommend is it doesn't hurt for you to write the initial momentum for one of them and put the plus 0. That sends a clear message to the grader that you know that you're supposed to check the other one, but you also know that it has 0 momentum. I think if you just had it where you started with this would also be perfectly fine to start with. But I guess momentum conservation should actually be P initial equals P final. But I think as long as you've got this out, you should be in good shape. Okay, moving forward. I want to try and get this isolated, so I get Vs equals some stuff. 1/2 m naught v naught. I'm going to add this to both sides to get rid of that, plus 1/2 m naught v naught. I got 1 m naught v naught plus 1/2. That's going to give me 3/2 m naught v naught equals 3 m naught Vs. At this point, I can divide both sides by 3. I can divide both sides by m naught, and that leaves me with Vs, the final speed, or I should say velocity, because that's what we actually get from this, is positive 1/2 v naught. They're both going the same speed, one of them forward, one of them backwards. That's what we got from this particular momentum conservation. Okay, with this, we're not done yet. We need the kinetic energy of disk S. Well, that would be 1/2 3 m naught times Vs, which is 1/2 v naught squared. I can square this out and we'd end up with 1/2 3 m naught 1/4 v naught squared. Multiplying all these out, I get 3/8 m naught v naught squared. That should be our correct answer. So our kinetic energy is this. We have derived an expression for that. Okay, looking at our grading rubric. So on this, 1 point for a multi-step derivation beginning with conservation of linear momentum. In this case, I was a little bit sloppy. If you are studying for an exam, upcoming exam in my class or AP exam, remember you should always write it clearly that you're applying conservation of momentum, though I think this line or this line would be perfectly fine, but you do want to make certain that you are clearly getting across conservation of linear momentum. The next thing that we would have is 1 point for a correct expression of the speed of disk, B2. For one of the following. I thought that there might be multiple ways for you to get the second point on this. Analysis showing disk R reversing direction after the collisions. The thing that I mentioned before, that you are keeping track of the direction, that disk R is going in the negative direction. You will get a very different answer otherwise. So that is one of the key things. The other thing that I thought might warrant it, I'm kind of torn between these two, is for a correct replacement of the masses for each object. So R was m naught and S was 3 m naught. So I kind of combined those where I think if you do, it's one of those or the other. So I went ahead and put both of them in there. They're both kind of key things that I think might very well show up for that middle point. 1 point for a correct expression of the speed of disk S after the collision. So once again, this is where the point for getting the right answer is coming in partway through. This is positive 1/2 V naught. So if you weren't able to get the correct answer but did the other things, you could get the first 2 points, and maybe even the 4th point. Let's see. Oh, I forgot to update this. I'll try and get that fixed up. But that should say point B4. For using an appropriate equation to determine the kinetic energy of disk S after the collision. In this case, our correct equation would be 1/2 mv squared, putting in the correct mass. In this case, I could also see them switching some of these out, where maybe the intermediate points are 1 for this one for this one, not for the correct expression, and then maybe for kinetic energy or something like that, and then 1 point for getting the actual full end correct expression. I could see it kind of coming in the middle there, but it wouldn't surprise me on this one. This one isn't that messy of a derivation that if they would require you to get the full thing in order to get full credit. But if you didn't get the full complete answer, don't worry, you can still get plenty of partial credit. Okay, part C. The graph shown in figure 4 represents the position as a function of time from t equals 0 until t equals t1 for each of the following: disk R, disk S, and the center of mass of the 2-disk system. On the graph shown in figure 4, draw 3 lines that represent the positions x of disk R, disk S, and the center of mass of the 2-disk systems as a function of time from t equals t1 to t equals t2. Distinctly label each line. So we have to draw some stuff and we need to add a label. Oh, I forgot to mention it in question 1. The chief reader reports are heavily recommending that you go through and you use a ruler. So make certain that you have your rulers ready on the exam. In this case, we are shown everything building up to the collision. Collision happens at t1, and they want us to do a mirror amount of time. So if this is 1 second, then this would be over to 2 seconds. So we have similar amount of time. Okay, the key things that I want to bring up. I want to jump immediately to what's happening with our center of mass. A reminder to my students, or if you're not one of my students, then I'll tie this together. When you're asked about things like the position of the center of mass, well, if you've got a bunch of masses all over the place, if you treat them as being inside a system, the position of the center of mass is the position of the system. The velocity of the center of mass is the velocity of the entire system. Now, one part might be moving forward, one part might be moving backwards. Imagine you got a bunch of people on a train, and the train's moving along at 60 miles per hour, and you have one person walking to the front of the train. Well, they appear to be moving faster than 60 miles per hour because they're walking in the direction of the train. You might have someone else walking to the back of the train. They might appear to be moving slightly slower than 60 miles per hour. These are all the relative vector things. That being said, the entire system is moving with the train at 60 miles per hour. That's the idea behind this. So whenever you see center of mass, position, velocity, or acceleration, what you should immediately think is, okay, I'm looking at not all the individual pieces, but what the total's doing, which is the key to this. This happens a lot, especially in AP1. They're checking for you all to know, if you can identify, that when you have your momentum conserved, well, as we said before, that's the total momentum of the system. The total for the system doesn't change, and therefore, when we're asked about the center of mass, it's not going to change. So I would line this up, and I would do my dashed line and continue it this way, and then I would end up marking that center of mass. In this case, in the time here, it goes up 1 unit, so it should continue up and end right about here. They didn't say that you had to do the dashed line, but I would almost extend it with the dashed line. Makes it easier to kind of see what you're doing, but definitely mark it with center of mass because you were told to label them. Okay, disk S wasn't moving, and then it starts moving in the positive direction, as we found out, so I need one that goes upward. Specifically, please note for the original velocity, we've got a position as a function of time. The slope of this graph gives you your velocity. In this case, we saw that V naught in a time of 2 units goes up 4 spots. So we would have a slope of 4 divided by 2, 2 basically. To have half of that, I need something that goes up 2 into, or a slope of 1. So the correct answer for S should come from here up to the top corner here. For disk R, we need it to reverse direction. It needs to have a negative slope because it bounces back the opposite direction, and it bounces back at half the speed, so we would have it go down to halfway the height, so it should end up over here. What does that look like? It looks like this. So here's what I think the correct answer would look like, properly marked with disk S, disk R, and center of mass. 1 point for a downward straight line marked for disk R with a shallower slope than before the collision. It's also possible that to get full credit, you might actually have to have it end right here at the halfway mark. I don't know, especially for AP1, they might have it where it's like, okay, you've got it where you've reduced the slope, so you know that it's going slower, but you wouldn't necessarily have to get exactly where the thing would go. I don't know. Again, this is a best estimate based on my years of experience with the materials. The second point, for an upward straight line marked for disk S that is greater than the student line for the center of mass, or one that goes up to the appropriate spot here. I say this because if the student ended up having the center of mass shallower, you might have disk S not nearly as much. The important thing that you can conclude is, since disk R is going backwards and the center of mass is kind of the weighted average of those two, disk S must have a greater slope than the other two, or at least positive. And then finally, for a straight line marked center of mass with identical slope to before the collision, extending that out. That's what the correct answer should look like and why it's the correct answer. Finally, part D, another one that I hope my students did very well on, because it says, during the collision, the magnitudes of the changes in momentum of disk R and disk S are delta PR and delta PS with absolute value, or more accurately, magnitude signs, because we're talking vectors, respectively. Indicate whether the impulse is greater than, less than, or equal to on R to S by writing one of the following. So this is one that I asked my students about quite a bit, and we looked at with multiple applications. If you remember the squirrel jumping onto the bird feeder, that was one where I was getting across the idea of the impulse on one object in a collision is mirrored by the impulse on the other. This one also asks you to justify by referencing a fundamental physics principle. There are two ways that I can think of doing this. Either by saying that our delta P total for our total system is equal to 0, and delta P total for the system would be our change in S plus our change in R. Now I'm going to put the vector signs on here because basically one of them would be opposite of the other. In order for my total to be equal to 0, then delta PS would have to be equal to negative delta PR. Now we can ignore the negatives because we are taking the magnitudes, but they must have the same values. Now, this is a mathematical approach. You could write this down, but this is just me representing it for you all to see. The actual description, what you would put in your justification, would be more along the lines of, our total change in momentum for the two-disk system must be 0 because the system's momentum does not change. That's what it means when you conserve the momentum. So that means whatever the change of one of them is has to be equal and opposite of the change of the other one, so that they would add together to be 0. Because they're equal and opposite, they would have equal value, and one of them would be negative, but then when you take the magnitude, the negatives drop out, and therefore they must be equal to each other. This would be a proof based on momentum conservation applied to our entire system. Or, as was presented in class, delta P is equal to our impulse, and that would be equal to our force times our collision time. Well, we have disk R and disk S. R experiences a force from S this way, and by Newton's third law, this is a action-reaction pair. However hard R hits S, S hits R just as hard. The force on S is equal and opposite to the force on R because they are a Newton's third law pair. That's another fundamental physics principle, Newton's third law, that I'm appealing to. When we take into account that our change in momentum is going to be equal to our force, which is the same for both of them, times the collision time, well, if R hits S for 1 second, then S hits R for 1 second. They have the same collision time. So by Newton's third law, our forces are equal to each other, and due to the collision, our delta t's, our collision times, are equal to each other, and therefore our change in momentum must be equal to each other aside from direction. So in this case, our magnitudes would be the same. Two ways to explain it the same way. Okay, so, or the same outcome. On this, I think I have both of those listed in there. I can't remember, but For a selection of the correct one where they equal each other with an attempt at a relevant justification based on physics principle. As I've mentioned in other spots, I don't know if they're still sticking with the attempt at a relevant justification. This is usually pretty common where it's like, did they get more or less the correct answer and did they try and give us a reasonable explanation on it? Even if the explanation isn't 100% great or even fully correct, is it something that seems like it would be pretty good, or is the beginning of a good argument? Then you can usually get the first of the 2 points. It depends on where they decide to draw the line on that, depending on if it's just attempt at relevant justification. Please remember, relevant means that you can't just go, well, I like R more, so it's got to be equal, at least the same as S. That doesn't make much sense. That's not relevant. But bringing in anything that's based on physics can probably get this point as long as it's reasonably applied, even if it's incorrect. Point 2, for a correct justification based on an appropriate physics principle. Here's where basically, if you got something that's a decent try at this, but it's not quite fully correct, you can get one of the 2 points. And the second point usually comes in for actually sticking the landing and making a really good argument based on the physics principle. I think that's how they would break down. You're also welcome to, I'm trying to link this down in the video comments, that sort of thing, but you can read through the suggestion that I have on this, but I want to keep these videos moving, even though they are still already kind of slow. All right, that was question 2, translation between representations. Hopefully you found it useful.